In this video, we're going to be examining two possible uses of the specific heat capacity formula we determined in the previous video, Q is equal to mc delta T. In the previous video, we looked at how this formula can be used to calculate the amount of heat is required to increase the temperature of water, but can this formula be used for other compounds? The obvious answer is, of course it can. Why can't it? The only variable that needs to change is the specific heat capacity, because obviously every substance is able to absorb a different amount of heat before its temperature increases. Nevertheless, the setup of our question is going to work exactly the same way, starting with Q is equal to the mass of the substance where we're increasing the temperature, times the specific heat capacity in joules per gram per degree Kelvin increased, times the change in temperature, usually in degrees Kelvin. Right off the bat, we can pretty much fill in all of our variables here. The mass of aluminum in this case that we're measuring is 120 grams, no fancy unit conversions needed. And then we're going to multiply this by the specific heat capacity of aluminum, which we see is significantly lower than water, 0.902 joules per gram of aluminum per degree Kelvin increased in temperature. We see that grams cancel here, and then a quick check of our delta T. We're going from 25 degrees Celsius to 100 degrees Celsius, which means that our change in temperature is going to be 75 degrees, and because 1 degree Celsius and 1 degree Kelvin are the same, this would be 75 degrees Kelvin. So if we put that into our formula there, we see that degrees Kelvin cancels, leaving us with joules. So if you put this into your calculator, you will get that this comes to exactly 8,118 joules. And since the question asks for kilojoules, and since we also need to consider two significant digits, we can make the rounding there. So again, we can do the conversion to kilojoules. We know that 1 kilojoule is equal to 1,000 joules. And if we round to two significant digits, this comes to approximately 8.1 kilojoules. So right there is the first easy example about how we can use Q is equal to mc delta T to calculate how much heat must be added to any substance in order to determine its temperature. The second application we can look at is in comparing different states of matter. Now, if we consider water, for example, do you think that ice, water, and water vapor all have the same specific heat capacity? Well, the answer to this is obviously going to be no. We know that air temperature changes a lot more quickly than water temperature does, so water vapor probably has a lower specific heat capacity than liquid water does, and conversely, ice will have a different specific heat capacity as well. So in answer to the question, does specific heat capacity get affected by state of matter? That's an obvious yes, and we can show this with our next application question here. So in this situation, we're taking a 750 gram block of ice that begins at negative 15 degrees Celsius, and we want to increase this temperature up to 22 degrees Celsius. But as we'll see, there are actually three separate calculations that we need to do, all because the state of matter matters. See what I did there? So, if we consider this process here, we can break this into three separate steps. The first is the heating of ice, and we can solve this now. We see that ice has a different specific heat capacity than liquid water does, but our formula works just the same. So Q, our total heat, is equal to the mass of the ice block, which is going to be 750 grams. Again, note two significant digits, and we multiply this by our specific heat capacity of ice, 2.05 joules per gram per degree Kelvin. And here, the careful thing we need to be aware of is that because ice has a different specific heat capacity than water does, we need to pay attention to the range of temperature that this block exists as ice, which is going to be negative 15 degrees Celsius up until 0 degrees Celsius. So therefore, we can conclude that our delta T is going to be 15 degrees Kelvin, because that's the range of temperature increase as long as we are dealing with solid ice. So we're going to multiply this by 15 degrees Kelvin, and right here, this tells us how much heat is required to increase the block of ice from negative 15 degrees to 0 degrees. However, at 0 degrees Celsius, something happens. That something is, of course, ice melting, at which the temperature remains constant. Now, what this means is that during the process of ice turning into water, the temperature of the substance does not actually change, but the amount of heat that we need to add to the ice is due to the amount of heat required to break the hydrogen bonds between water molecules in ice in order to get it to turn into a liquid. So because we're not actually increasing the temperature here, we're just undergoing a state of matter change, you can see that there is no delta T or no temperature measurement here. So we see delta T is not in the formula here, and units Kelvin is not in the formula here, which means all we need to do is take our specific heat capacity of the state of matter change, which is what we call heat of fusion, and multiply it by the mass of the ice block, which would be 750 grams times the heat of fusion, the heat required for a state of matter change from solid to liquid, which is 333.55 joules per gram. And right now, if we add these two totals together, what we have got is the amount of heat required to increase the temperature of ice to 0 degrees and then melt the ice. So the third stage is the heating of liquid water. So if we look at the temperature that we need to get liquid water to, we see that we need to bring liquid water from 0 degrees Celsius up to 22 degrees Celsius, and therefore our delta T is going to be 22 degrees Kelvin, and that allows us to complete the third step of our formula, which is 750 grams for the ice block times the specific heat capacity of liquid water, 4.184 joules per gram of water per degree Kelvin increased, times our temperature increase, which is going to be 22 degrees Kelvin. And again, if we add these three steps together, we show the total amount of heat required to increase the temperature of the ice block, melts the ice block into liquid water, and then increase that puddle of liquid water up to the requisite temperature. If you put this into your calculator, you will find that this number comes to approximately 342,262 joules. Actually, it's not approximately. This is the exact number here. Again, we take note from our conditions here. We see that our final answer is going to be with two significant digits. And remember that the question asked for kilojoules, so we can make those quick unit conversions here. So 1 kilojoule is equal to 1,000 joules. And if we do that, and if we reduce to two significant digits, we find that this number comes to approximately 3.4 times 10 to the exponent 2 kilojoules, which is, again, quite a lot, because regardless of what the state of matter of water is, it requires quite a lot of heat in order to undergo any temperature change at all. Now, if we refer to this graph here, at every one of these locations here, that represents one of the steps that we showed. So at 1, this is where the heating of ice happened, and then at stage 2, we see that the temperature remains constant here, which corresponds to melting, and then stage 3 here describes the process of heating liquid water, because again, we see the temperature range go from 0 degrees to 100 degrees. Now, if we kept this going, if we wanted to show what would happen to water if we get it above 100 degrees, well, we know at 100 degrees Celsius, water evaporates and water turns into water vapor. And just like with the process of melting, where we consider heat of fusion, the temperature at this point remains constant because, again, we're not increasing the temperature here. We're adding in heat in order to break the hydrogen bonding that keeps water in liquid form, which, again, is why we call this the heat of vaporization, because because this is the heat required to convert liquid water into water vapor. In the next video, we're going to look at how our specific heat capacity formula can be used in order to calculate the energy change that occurs within actual chemical reactions.